Welcome back to our fundamental concepts in chemical engineering. Today we're going to be covering energy balances, and this will finish our unit on mass and energy balances. By the end of today, you should be familiar with thermodynamic quantities. You should feel comfortable with the definition of open and closed systems. You should be able to consider doing energy balances in non-reactive systems, considering phase transitions, and energy balances in reactive systems. Let's start out by considering what are we going to call energy. So the total energy of the process, or of a process stream, the total energy in something, is going to be the kinetic energy plus its potential energy plus its internal energy or enthalpy. And we'll get into the difference between the internal energy and the enthalpy in a little bit later. In this class, we're going to assume that the kinetic energy in any system is only from translational motion. So, velocity of systems, so think flow through a pipe. And potential energy is only from gravitational forces. I also want to make a comment that throughout the rest of this class in chemical engineering and chemistry in general, we're going to consider that delta, which is this sort of triangle, shows a change in, right? So if I look at a change in internal energy, I'm looking at the final minus the initial, right? So final minus initial, this is always how we're going to define the change, right? And so the sign of delta U is going to indicate the direction of our energy flow. Negative means flow out, and positive means flow in, right? So if delta U is positive, energy has gone into the system, whatever I'm looking at. If delta U is negative, energy has come out of that system. All right, so let's do some additional definitions of energy transfer, not in terms of kinetic or gravitational energy, right? Those hopefully you feel comfortable with from physics, right? To increase the kinetic energy, I speed it up. To increase the potential energy, I move it uphill. But mostly in chemical engineering, we're interested in two energy transfer mechanisms, so heat and work. So heat, which we'll refer to as Q, or Q dot if it's in terms of a rate, is the energy transferred due to a temperature difference. So it's energy that's coming in because energy is going to flow from something hot to something cold. Okay, so if I think about a sort of a system block and there's some temperature outside of a system that's warmer than T0, heat is going to flow into that system from the surroundings. But if the T outside this block is lower than the temperature of the block, it'll flow out. So think of it, right, if this block is, say, an oven, and it's at 200 degrees Fahrenheit, that's warmer than your room. So heat is going to move from the oven into the room. Or conversely, right, you have your freezer. The freezer's colder than the surroundings. Heat is going to flow into that freezer through the walls of the freezer unit. So we can also do an additional, we can also have an additional type of energy transfer that we shall call work, that we'll denote as W. And so W is the energy transferred in any other way. So this is energy put into a system through mechanical motion. So think, say, a pump or a turbine, or some sort of electrical current, think, electrical heating. And so we define W as positive when work is done by the system on the surroundings. So W is positive when energy moves out of that system. And work is negative when the surroundings puts energy into our system. Okay, so I'd like to sort of define two types of systems that we're going to encounter in engineering. So one is an open system, and that means that mass is moving through our boundary in time. So think about this as like a continuous process, right? So there can be stuff is flowing into a reactor, stuff is flowing into a flash unit, stuff is flowing in and out. A closed system, it means that material, so matter, doesn't move through the boundary. So think like closing a soda bottle, right? That soda bottle is a closed system. Whatever's happening in there, we have a batch process. All right. So if we think in terms of energy transfer, the change in internal energy, if I don't have any change in the kinetic or potential energy of the system, so delta U is equal to the heat that I put in minus the work. Easy peasy. So let's consider first a closed system, right? So I have a piston with some sort of fluid in here, right? This is a closed system because this fluid, in this case water, isn't moving out of this piston. It's always contained within the piston. If I were to put heat into this system, so Q is positive heat is moving in, the temperature of this water rises from say 0°C to 100°C, maybe vaporizes, right? So Q has been put into the system and work has been done by the system. There's expansion, so work is positive. Okay, so I want to provide another slight modification that we'll see a lot in ChemE and engineering in general is the enthalpy H, which you're probably used to, is the internal energy plus PV, right? So this is essentially the work done, PV being pressure and volume. This is the work done to create the space in order to give your material a space to reside. All right, so just like before, and we can look at, we can do an energy balance, right? The accumulation, this is our fundamental equation of chemical engineering. Accumulation is input minus output plus generation minus consumption. I can wrap this all down into here, right? So what's the change in the chemical potential of my system? What's the change, sorry, not in the internal energy of the system, what's the change in the kinetic energy, change in the potential energy, and that's equal to Q minus W. This is easy because energy can neither be created nor destroyed, as long as we're not dealing with nuclear systems. Okay, so if our system is not accelerating or decelerating, then our change in kinetic energy is 0. If our material or system is not moving up or down, then the change in the potential energy is 0. If we have no reactions, no phase change, no temperature, and or only a small pressure change, the delta U is 0. If a system and the surroundings are at the same temperature, or we have perfectly insulated, we're going to call this an adiabatic process. So, delta U might not be 0, but delta Q would be 0. Work done on or by a closed system is accomplished by changing the system boundaries. Therefore, if there's no moving parts, right, so there's no turbine, there's no pump, then our work is going to be 0. So these are just a few keywords to be looking for and thinking about when we think about energy balances, so that we can think about which of these terms should be 0. Okay, so once again, I want to talk just a little bit about definitions. In SI units, we think about energy. If I think about power, that's going to be a joule. Sorry, if I think about energy, that's a joule in SI units. If I think about power, that's a watt, which is a joule per second. A batch process, right? We're not thinking about how much, it's just the total energy going in. In a continuous process, we want to think about an energy demand rate, or how much power, how much energy per time is going in to a system. We're going to define that as a watt, which is a joule per second. Lastly, I'll make a quick comment on efficiency. This is going to come up a little bit later in this course. And usually we say something, how efficient something is the energy put in to a system versus the desired change in a process, right? So if I have a turbine or a pump, those aren't 100% efficient, so energy is sort of lost to the surroundings. All right, so oftentimes what we're going to see in thermodynamics and mass and heat transfer, etc., we need to find out what are the energies of materials. And we often get these from thermodynamic tables. And so these are going to provide us information about a system. So here I'm showing a steam table. So this gives me the properties of saturated steam. And what we'll find in here is all sorts of information that's really useful in doing energy or energy balances, or really any sort of thermodynamic analysis of a system. So over here, we have the temperature, this pressure, right? I have thermodynamics, saturated steam. So this would be the pressure, equilibrium pressure above water at that temperature. And then I have these three columns. So first I have my specific volume. So how much space is taken up by a kilogram. So you'll see water. This is that 1 kilogram per liter, a sort of unit. Steam obviously is much bigger. It takes up way more space per kilogram compared to liquid water. I also have the internal energy and the enthalpy. And we'll see that a lot of times these thermodynamics are all referenced to 0 degrees C. However, it's important to look and always find out where our material is referenced to. Okay, you'll see that if I look between water and steam, there's a massive energy input to heat the steam, to heat water into steam. Okay, and as temperature increases for both water and steam, the energy of the system goes up. You'll also see, if I look at delta H, that I have, so I have both U and delta H. And if you look at the water has, there's not much of a difference between U and H, right? This is because, of course, the difference between U and H is H has U plus PV. And the specific volume here is very small, right? So this volume, that V part of PV, is essentially 0. So there's no difference here. But in terms of the steam, there is a significant difference, and that's coming because that volume of the steam is no longer negligible. Oftentimes, what you'll see when we look at these tables is we have not only the water, the liquid and the vapor versions, but you'll also often have an enthalpy or a heat of vaporization. So this is just the energy difference between the liquid and the vapor enthalpies. If you're looking at something that may be changing phase between a solid, liquid, and gas, you may have a third column that would, in this case, be ice, and have these same pieces. And then you would have not just the evaporation, but also the heat of melting. All right, so let's do a practice problem. Let's determine how much heat must be added to a sealed vessel containing 2 kilograms of water at 2C if we want to end up with saturated steam, if we have saturated steam at 10 degrees C. We're going to assume that the entire system, there's no real change in volume. All right, so we can do this. We can look at our energy balance. So delta H plus delta E plus delta EK, the kinetic energy plus the change in the potential energy, is Q minus W. All right, so let's go through these terms. Is there some sort of change in the enthalpy? Yeah, probably, because we're having a change in phase and a change in temperature. So this can't be zero. It's very unlikely to be exactly zero. We can then look at the kinetic energy. Is my system moving? No, that's zero. Is my system moving up and down? Is it being lifted up? No, this term is zero. Is heat going in? Well, probably because we're being asked to look at how much heat needs to be added. And then lastly, am I doing any work? Well, in this case, no, there's this vessel sealed, nothing's moving in and out. The vessel isn't contracting or expanding. That's zero. All right, so we're left with a relatively simple equation. The change in enthalpy must be equal to Q. So the change in enthalpy is, of course, final minus initial. So the enthalpy at the end minus the enthalpy to start. I can go to my tables. I can say, okay, hey, I know at the beginning I have water at 2 degrees C. So I look up 2 degrees, move over to the water, and I find that that has an enthalpy of 8.4 kilojoules per kilogram. I know at the end I have 2 kilograms of steam at 10 degrees C. So I go down to 10, run over to the steam table, and we have 2,520 kilojoules per kilogram. Okay, so now I just need to plug that in. I have 2,500 kilojoules per kilogram. I have 2 kilograms in my system. At the beginning, I have 8.4 kilojoules per kilogram. I have 2 kilograms. So in the end, I need to put in 5,000 and change kilojoules. All right, so this is an example of how I would do an energy balance on a closed system. I can do something similar if I have an open system. So let's say we have steam that's being used to drive a turbine. The steam is going to enter my system as a saturated vapor at 200 degrees C, and then it's going to leave my turbine at 100 degrees C. A condenser then cools the steam down to room temperature. We're going to be asked to determine the work and the heat that's removed from this system. Okay, so just like our mass balances, the first thing that we need to do is draw a picture. So here I have, I have 2 processes. I have a turbine, right? That's this first thing, and then I have a condenser, so I can draw a box and have my condenser. I'm going to label those so I know what units I've got going on. I have steam that's entering my system at 200 degrees C. I want to note this in my diagram for use later. My turbine, right, that's there to extract work. So I know that work is happening in my turbine. I'm going to assume that that turbine is adiabatic. And I have steam that's coming out of the turbine at 100 degrees C, right, because the problem statement tells me so. I'm going to enter a condenser. The condenser is going to be no moving parts. I'm just sucking heat out. So Q is going to come out, and then I'm left with water at room temperature, right? Because that's what exists at room temperature is liquid water. All right, so I've moved my diagram up here. Now we're ready to start my energy balances. Notice that I have quite a few places. I have three energy balances that I could do. I could do an energy balance over the entire system. I could do an energy balance over the turbine or the condenser. First, if I just analyze the system, I can see that I know how much energy comes in as steam and leaves as water, and I know that I have both work and I have work and heat that I can use, but I don't have a way to directly determine how much comes out as work or Q. So I'm actually going to start my balances by looking at each of these individual units. And so let's do the turbine first, as it's showing up first in our system. All right, so here we have our energy balance. Again, I can look at which of these I can keep and which I can throw away. Our kinetic energy, there's no change in the kinetic energy, right? There's nothing that says I have a change in velocity. I have no change in pressure or in potential energy. I have nothing moving up and down. And in this box, I have no Q. I'm going to assume it's adiabatic. So I've now simplified my energy balance to say that the enthalpy, my steam out minus the enthalpy of my steam in is going to be negative W. Okay, so just as a point of basis, I can assume that I have 1 mole per second, just so I can put this on some sort of basis, consider what's happening. All right, so again, I can pull numbers from a table. Here I've pulled them and organized them. Here's 200, 100, and 25 degrees C. I have the enthalpy in liquid and gaseous phases. And so I can plug those numbers into my equation. So the H out, I've got steam at 100 degrees C, so I can go to my table. I have 100 degrees C, steam, that's the gas phase, right? It's 84.18 kilojoules per mole, okay? I have 1 mole per second of that flow. What went in? Well, I was steam at 200 degrees C. That's 49.84 kilojoules per mole. We can do the math out, and we find that the total amount of work we can extract from the turbine is 1.66 kilojoules per second, or 1.66 kilowatts. Okay, now notice that this is a positive number, and by our definition, a positive number is when the system, right, the steam does work on the outside world, right? So this, we're able to extract 0.66 kilowatts from this turbine. Okay, cool. So now we've got W under our belt. Let's look at Q. Let's pick our system boundary. We can look at the condenser. We're going to end up with the same equation, but now what's coming out is going to be our water at 25 degrees C, and what's moving in is our steam at 100 degrees C. I can go again with my basis. What's coming in is steam, so I use this gaseous quantity, 48.18. And then what's leaving is water at 25 degrees C. I use the liquid water portion. I plug that into my equation. Given 1 mole of H2O per second, I have a Q of negative 46.22 kilojoules per second, or negative 46.22 kilowatts. So heat is coming out, and work is being done by this system. Okay, so this shows you how we can do energy balances on both open and closed systems. Sometimes we don't have tables, but we might have heat capacities. So a heat capacity tells us how much energy it takes to change a certain amount of material. So how to relate the energy flow associated with the temperature change. So my change in enthalpy is the integral of this quantity called heat capacity. And here I've written it as Cp, so the heat at a constant pressure as I change my temperature, right? So oftentimes if this change in temperature is small, or heat capacity doesn't really depend on temperature, we might often write the change in enthalpy is my heat capacity times the difference in these two temperatures. Okay, this is usually an okay approximation if I have solids or liquids, or if I have a small, if I'm looking at a small range, temperature range in a gas. All right, so heat capacities usually are complex functions. And you'll learn a little bit about where this comes from and why these are functions of temperature in our core course on graduate level thermodynamics. But for right now, let's just know that in most cases, these heat capacities are written out as a function of temperature and are often done as a polynomial. And I can look up in tables, just like I could look up enthalpies or entropies. I could look up the heat capacity in a table, and they're often given in terms of, they'll tell you what the form of the polynomial is, and then what the coefficients are. And then they'll often state what the units would be, right? So these would be an okay set of parameters to use over, in this case, from 0 to 1200, and in the units of Celsius. When you're reading these tables, always make sure that you're paying attention to what state you're in. So whether you're in the gas state or the liquid state, because they're going to have different sets. And then if they give you multiple forms of equations, which equation you're using, and then really, really, really importantly, whether you're operating in Celsius, Kelvin, Fahrenheit, Rankine, whatever. Okay, so my last sort of comment on specific heat for a single material is you can also specify specific heat at a constant volume. So you put a material in a canister, you don't let it expand, and you see how much energy it takes to change the temperature. This would be specific heat at constant volume versus specific heat at constant pressure. You'd allow the volume to change so that the pressure inside remains constant. In liquids and solids, the heat capacity at constant pressure and the heat capacity at constant volume are approximately equal. For an ideal gas, the heat capacity at constant pressure and constant volume can be related by this inclusion of R, our universal gas constant. If I have a mixture of liquids or gases, we need a way to combine the effects of both. In general, we approximate the mixture of gases or liquids as a weighted average of the components. So we just take the mole fraction times the molar heat capacity, or the weight fraction times the specific heat capacity. Often, if I have dilute mixtures, so if I have very small amount of CO in a bunch of CO2, it usually doesn't really change things. So I just neglect the minority component. Okay, so these are approximations because we're sort of ignoring effects of mixing, but usually that's a pretty good approximation. All right, so if I go through, and we saw this a little bit before, if I have heating that's going to send me through a phase change, I can't use just the heat capacity of the liquid or the gas, or the solid and the liquid. I have to use sort of a compound change in enthalpy, where I use the heat capacity of the first phase that will take me from whatever temperature I'm starting at, move up to the temperature of the phase change, then take into account the phase change and enthalpic change, and then do whatever secondary temperature change that I'm interested in. Because this is so commonly done, oftentimes you'll see you'll look up you can look up what these delta H's of phase change are. Here I'm just showing again an example. Here's a temperature of heat of melting, as well as the temperature of that melting, right? So this phase change for acetic acid is at 16.6 degrees C, so that would go here and here. And then I would use this delta H of melting, and I could read that off the table. All right, so this brings us to our sort of another concept that's really important in thermodynamics and that we'll make use of, is that the total enthalpy change of a system is independent of our individual steps. So let's say I have some sort of process that I start with material A and I go to material B, or start A, go to state A and I go to state B. This change in enthalpy is the same, is equal to the change in enthalpy if I go through sort of these three steps of saying, well, first A goes to B, then B goes to C, then C goes to D, right? So I'm path independent. Okay, now that we've sort of got all these ideas, let's look at one example that's going to consider these processes. And this is going to not only integrate some of these concepts that I talked about in terms of energy balances, energy balances, and sort of complex changes in temperatures, but also is going to pull in the integration of mass and energy balances. So let's consider a reverse water gas shift reaction. We're going to have 1 mole per minute of both CO2 and H2 being fed into a reactor, and they're going to enter that reactor at 700 degrees C. We're going to end up with a mixture of CO, CO2, H2, and H2O. And those are going to leave the reactor at 850 degrees C. Notice I'm not telling you what the reverse water gas shift reaction is. We don't need that information. We're going to be able to figure that out. To this reactor is supplied in a secondary heating coil 5 moles per minute of saturated steam. The saturated steam is going to enter our reactor at 1100 degrees C and leave at 900 degrees C. If the enthalpy of the reaction is plus 41 kilojoules per mole of hydrogen consumed, how much water and CO are produced? Right? Here's our problem statement. It seems quite complex, and that's sort of because it is, but we can tackle this using the information that we've covered already today, as well as what we've covered in the previous 2 lectures. So of course, let's first draw a picture. So here I have my reactor. I know that I have hydrogen and carbon dioxide entering the reactor, and it's entering at 1 mole each, so that's 2 moles per minute, and they enter at 700 degrees C. Here I'm labeling the temperatures because if I'm going to have an energy balance, it's just useful to have all that information together. They're going to leave the reactor at 850 degrees C. That reactor is at 850 degrees C. I don't know how much is leaving, and I don't know the mole fractions of these systems. I also had steam that was providing heat through a heating coil. I have steam entering at 1,100 degrees C, and that's entering at 5 moles per minute, and then steam leaving the reactor at 900 degrees C, also at 5 moles per minute. Okay, so we have everything labeled. We have our picture that's going to live up over here. And the first thing that we're going to do is do a mole balance to try to situate where we are, and then we'll do an energy balance. Okay, so let's start by looking at our molar balance of the steam system. You can sort of look at this over here because it's a little bit easy. I've got the steam going in, the steam coming out. It's 5 moles per minute, easy peasy. Now, let's look at this other stream. Right, so this other stream, right, that we could think of as our boundary is our streams 1 and 4 in our system. I want to start by doing, right, we have choices here. We can do a mole balance or we can do an atom balance. Here we're going to end up doing both, but I'm just going to start with our atom balance. Here I've just labeled H2 on the top of my list, so let's start with our atom balance for H2. Right? So how many moles of hydrogen atoms are generated or destroyed? 0. How many are going to accumulate in our reactor? 0. Therefore, we should have 0 equals the moles of hydrogen atoms in minus the moles of hydrogen atoms out. So how many moles of hydrogen atoms are going in? Well, I have my inflow into this system, so that's 2 moles per minute. 50% is H2, so I multiply by 50, and I have 2 moles of hydrogen atoms per mole of molecular hydrogen. Now I can look at what's happening on the out phase. I know I have N4 moles per minute of H2 leaving, and then I have, for every mole of H2 leaving, I have 2 moles of hydrogen atoms. And then I have N4 moles per second of water leaving. And I have, again, 2 moles of hydrogen atoms per mole of water. So I can simplify this equation, and I'm left with 1 equals the molar flow rate of hydrogen in stream 4 plus the molar flow rate of water in stream 4. I can do the same thing with doing a carbon balance. Again, I have 2 moles per minute of CO2 entering the system, that 50% of which is CO2. There's 1 mole of carbon per mole of CO. And then leaving the system, I have molar flow rate of CO in stream 4. I have 1 mole of carbon per mole of CO. And then I have, sorry, this should be a CO2. And then I have a flow rate of the CO2, 1 mole of carbon per mole of CO2. So in the end, if I do out this math, I'm left with 1 equals the molar flow rate of CO in stream 4 plus the molar flow rate of CO2 in stream 4. And then lastly, I can do the same thing with oxygen, and I'm left with 2 equals the molar flow rate of CO leaving in stream 4, 2 times the molar flow rate of CO2 in stream 4, and the molar flow rate of hydrogen of water in stream 4. So if I look at this, I have 1, 2, 3 equations, and I have 4 unknowns, right? I don't know how much hydrogen, how much water, how much CO or CO2 is in this stream 4. So 3 equations, 4 unknowns. I don't have enough information. I can't solve my mole balance or my atom balance. Okay, we can try this again with a molar balance instead. Maybe we can get enough information there. So let's do my molar balance on H2. Accumulation is 0. What's flowing in? 2 moles per minute times 50%. What's leaving? My molar flow rate of hydrogen and my molar rate of hydrogen. How much is reacting away? Well, there's some amount of hydrogen that reacts. I don't know what that is. I can rearrange this though, and I can find that 1 equals the molar flow rate of hydrogen leaving plus the amount of hydrogen that reacted. I can do the same thing for CO2. It's going to look pretty similar. 1 is going to equal my molar flow rate of CO2 leaving plus the number of moles of CO2 that reacted. In terms of water, I had no accumulation. I have no moles coming in, but I do have moles leaving. So that's my molar flow rate of H2O plus how much it was generated. So this is the number of moles reacted in this case. And I can do the same thing for CO. In this case, I have three equations, and I don't know, sorry, 4 equations. 1, 2, 3, 4 equations and 8 unknowns, because not only do I have the species, but I don't know how much each of them reacted. So I'm almost worse off than I was before. This is where energy balances are going to come in and help us to determine how much reacted or how much energy there's available to drive this reaction forward. Okay, so I'm going to just write down some of these equations that we've talked about over here. Here I'm just showing the atom balances for hydrogen, carbon, and oxygen, just to save space. So these are the equations that we're going to use in a little bit. I'm just going to keep them over to the side. All right, so let's do an overall system energy balance. So overall, we have energy that's coming in minus energy that's going out. Energy that's going out minus energy coming in, right? So final minus initial. What's leaving? Well, that's stream 4 and stream 3. What's going in? That's stream 1 and stream 2. And that must be equal to the heat that's moving into the system and the work that's coming out of the system. Now, considering I drew my box around this entire system, and we are told that any additional energy is being provided and no work is being done, both of those, Q and W, are 0. Therefore, I'm just left with the enthalpies of those streams in and of themselves. What you should immediately notice is that I have temperature changes which are happening. Right, the steam is decreasing in temperature. Here, I have a bunch of reactants which are having to increase in temperature as it moves into the reactor. So we should think immediately, okay, I have temperature change, therefore I need to look at heat capacity. I'm providing here a table of heat capacity and an associated polynomial. So here we have A, B, C, and D that will fit this polynomial. I'm given that this is a heat capacity at constant pressure in joules per mole K. And I have 4 different species, so all of the species that we might use, so that's CO, CO2, H2, and H2O. And we're told that the temperature needs to be in Kelvin for this as part of these units. Okay, so let's go and let's start thinking about our system, right? I need to know, what's going in, what's coming out. I want to start, so let me go back. I want to look at this equation in my energy balance. I know that I have sort of this 2 and 3. I'm going to just start out by looking at 2 and 3 because that's going to be the easiest piece, right? I know the most information about that, right? I know how many moles there are, and I know what the temperature change is. So let's see if we can look at that steam system, right? So I have N3 minus N2 is the delta H of that steam. And from the definition, it's our molar flow rate of the steam times the integral from T1 to T2 of the heat capacity. Right? Here's this chart down here that we're going to use to fill this in. So I know in terms of my delta H of steam, I'm starting from 1100 C and I'm going to 900. So I have my integrands on here is 1100 to 900. Note, it's really important that we're using where we started and where we end up, not, low and high. It's not low and high. It's where we start and where we end up. All right, so I'm now going to take this equation for our heat capacity. Because we don't know how much it's going to change, I need to put this whole thing into my integral. So here I've taken my heat capacity, I've plopped it into this integral, and notice that I'm going to have to change my integrands because this table was laid out and we were told that these are the values in Kelvin. So I have to add 273 to my integrands. All right, so I can go ahead, I can use calculus, which you should all be familiar with, to take the integral of this polynomial. I'm left with 1/4 at to the fourth plus 1/3 bt cubed plus 1/2 ct squared plus dt. And that needs to run from 1373 down to 1173. Okay, I can take this equation, I can go down, this is my steam, I can look up my values for A, B, C, D, and plug them into this equation. And I now am left with just some nasty algebra to plug through. This whole integration term ends up being negative 8.9 kilojoules per mole. What's the molar flow rate? Well, that's 5 moles per minute. So my change in enthalpy of this steam loop is negative 44.56 kilojoules per minute. That was a lot, right? That was just a lot of plugging and chugging, but we now know how much heat is lost by this steam loop. Okay, so let's go back, do our energy balance. We can look up here, right? Earlier I had HN4 plus HN3 minus HN1 minus HN2, but we know what HN3 minus HN2 is, and that's equal to negative 44.56 kilojoules per mole. So I've replaced that, and we're now left with this simplified equation. All I need to know is what HN4 minus HN1 is. Okay, so let's determine what needs to happen. Well, here, I'm going to again use this idea of our Hess cycle, right? So remember, I'm path independent. So what's happening in this reactor? Well, this stream needs to be heated from 700 to 850, and then I need to undergo a chemical reaction. Note that it doesn't matter if I consider, well, maybe there's a chemical reaction and then I heat, or it heats up a little bit and then it reacts and then it heats up again, right? I'm path independent. So how we can write this is I'm going to heat up. For simplicity, I'm going to assume that we're just going to heat up the hydrogen first. from 700 to 850. Then I'm going to heat up the CO2 from 700 to 850. And then finally, I'm going to undergo my reaction, which is going to release or consume heat. Okay, so we have three components to this part of my energy balance. And we're going to tackle each of these pieces one at a time. All right, so let's tackle first this temperature change. So my temperature change of heating the hydrogen is going to look an awful lot like the temperature change associated with the steam. So in this case, I have my molar flow rate of hydrogen. I now am taking my integral this time from 700 to 850, right? Because I start at 700, I'm going to go to 850C, and then I'm going to correct that by this plus 273 in order to move to Kelvin. I then have my polynomial. I can take my integral just like I did before, and I'm going to cut to the chase here a little bit. This integral ends up being 7.4 kilojoules per mole H2. All right, and so once I take into account that there's 1 mole of hydrogen per minute flowing through the system, I now can fill in what this term up here is. Okay, and so I've done that. So this delta H step of this overall piece, we have this 7.4 kilojoules per minute. And now I just need these other two pieces, the enthalpy change associated with the CO2 and the enthalpy change associated with the reaction. Let's next tackle the enthalpy change associated with the CO2. This is again going to look very similar to the H2. I have my integral, and now I'm going to go down to my table. I'm going to pull in the information associated with the CO2. This time, when I do that out, I should end up with 7.3 kilojoules per mole. I can plug that into my total H step. This must be HN4 minus HN1, so I can plug this equation into these sets here, and I'm left with a final energy balance that says 7.4 kilojoules per minute plus 7.3 kilojoules per minute plus N react times delta H react minus 44.56 kilojoules per minute must be 0. Right? So this is the energy balance on my entire system. So all of a sudden, we've gone from something that's really complicated, right, from reading that initial problem statement into something that feels much more manageable, right? I only have one unknown left in my system. This is because, sorry, I only have one unknown or two unknowns, right? N react and delta H react. So I can, do some simple arithmetic and end up with the fact that N react times delta H react must be 29.86 kilojoules per mole. Now, if you remember the problem statement, we actually already know what delta H react is. We were told that delta H react is 41 kilojoules per mole of H2 that reacted. So when I do that algebra, we know that that 0.73 moles of H2 react per minute. Okay. Wow. Hey, so from our energy balance, we're not only able to tell how much heat moved from the steam, but we were able to see how much of our reaction happened, right? We can know how much H2 is reacting per minute, right? We're told right here, just from the energy balance. Okay, so let's combine our energy balance information, so N react, in conjunction with all of the different versions of the mole balances and atom balances. right? We now sort of have too much information, but I'm going to lay them all out here because we're going to want to pick the things that look easiest to solve, right? So let's look at this. I know what my moles of H2 reacted are. I can scan through the system and see what's most useful, right? What's going to solve my simultaneous equations most simply. And it's this first one, right? Because I only have, once I recognize that we know how much H2 reacted, I'm only left with one unknown, right? I can plug the that reacted H2 in there, do some algebra, and then we find that the number of moles of H2 leaving the system, leaving on the right-hand side, is 0.27 moles per minute. Right? So I can now put that over here, right? I now know that. I can now scan through my system. What's the next easiest thing that's got the, that's going to contain N4H2? Well, it's this equation down here, right? There's only one other unknown. I can substitute in my knowns, again, do algebra, and I find that I have 0.73 moles of water per minute leaving through stream 4. Okay, once again, I can clean up my equations. I can look through the system. The system that is most beneficial is plugging in down here. I then can see that, hey, I don't have a simple solution. I need more information. Well, looking through the equations that I haven't used yet, I can see that I have this equation right here, 1 equals N4CO plus N4CO2. Hey, these unknowns are the same as the unknowns here. 2 equations, 2 unknowns. I can substitute this top equation into this bottom equation to get one equation with one unknown. And so all I've done is substituted into here. I rearrange, do the algebra, and I find that the moles of CO2 leaving the system is 0.27 moles per minute. Okay, I now know how much CO2 is leaving the system. I can then solve this last equation and find that the number of moles of CO leaving is 0.73. Okay, so here's all of my molar flow rates. And then not only have I now sort of solved my problem, right? I know what all of my molar flow rates are leaving, which is fantastic, but we can also see that the reaction must be a 1-to-1, right? CO and water are formed in the identical, CO and water are formed in the identical ratio. We can also see that the amount of H2 and CO2 consumed is the same, and it's equal to the amount of H2O that was formed, right? So this must be the reaction. So just by doing a mole balance and an energy balance, not only have we solved what's leaving this system, but we can also discern what's happening in our reaction. All right, so what did we do? We are able to solve how much water and CO are being produced, right? So we did this as just a reminder of reading the problem. We drew a picture. We did an initial mass, mole and atomic species balance that did not provide us enough information. So we had to go to energy balances. We did an energy balance on the steam stream, and then we did an energy balance on the reacting stream. That reacting stream, we had a temperature change and a reaction. We took into account the energy change from temperature using heat capacity. And from that, that was able to tell us how much energy was going into the system to run the reaction. Because we knew what the enthalpy of reaction was, we could then backtrack exactly how many moles reacted. And once we knew how many moles reacted, we could solve out the whole molar balance. All right, so hopefully now you feel comfortable with integrating thermodynamic quantities into mass and energy balances. You know what the difference is between a closed and open system. We showed you examples, and you should feel comfortable with energy balances on systems that are not reacting. You should feel comfortable with doing energy balances on systems with phase transformations, and then you should be able to do energy balances on reactive systems. Of course, like we showed in that last final example, these often require coupling to mass balances. By coupling both mass and energy balances, we can discern massive quantities of information about how a chemical system is behaving. All right, with that, I hope you have a lovely day, and we will see you for next time, where we'll be talking about fluid mechanics. So moving out of sort of our intro phase and into our first examination of transport.